Test. Okay. Hi, good morning, everyone. There are about 80 of you. I will start by revising last week's materials while we're waiting for the others to come. Okay, take out your clicker and tell me something about PS1 later after this. So some admin slides first. At the moment, everyone already have a lab and tutorial group. So hopefully there is no more requests to change or join other group. And tutorial starts, both tutorial and labs starts this week. And even some tutorials start today after lunch. Right, so if you have Tuesday tutorial, remember that your first session will be today. Then, just now I checked, it's about 123, but not everyone. So there are 141 2010 students and about 12 something 2010R students who are not in 2010 this semester. So about 153 students, only 120 something have registered. How about the other 30? So if you haven't done that and you are in this room, can you do that now? Because if you don't do it, you can't download PS1. And once everyone downloaded PS1, then we will open the submission system. Let's take a look at PS1 briefly. So when you download PS1, you will see a zip file containing these files, right? You have one PDF, two sample skeleton files, and several test cases, sample test cases for you to try. And when you open the PDF, you will see something like this. Let me enlarge it. Okay. So it's supposed to be open today, but I have opened it 1.5 days ago on Monday night. If you noticed that, some of you noticed that. And it will be only due about 1.5 weeks away from now, Saturday, 8th September. So you have about almost 2 weeks, let's say 1.5 weeks to discuss how to solve this problem. Right? So look at the collaboration policy. I highlighted this again. Right? You are encouraged to work with other students. It's very different, right, from any other modules. You are encouraged to discuss. And you can also discuss with teaching staffs inside or outside this module on solving this problem set. The only thing that you have to do by yourself is you code it by yourself. You can discuss, but you cannot copy other people's code. You can only, you have to write it yourself. Okay, and then if you discuss, mention the list of collaborators. Right? And this list includes, if you read some other posting from certain IVLE discussion forum thread, you think, I want to use that idea. Then that idea doesn't come from you originally, and mention it. Okay. All right. The total percentage of this lab component take-home problem set is only 15. If you caught cheating, violating these principles, you will be referred to the NUS Board of Discipline. If you are not caught, you get this 15%, but then if you don't get the knowledge from this exercise, you will lose out in the other 85 because our quiz and final exams will be relevant with our problem sets. Right? Then some of you who took our option, where is it? It's at the back of this page, of this file, at the very back. Okay. So there are questions. Should you do it or not? For 2010R students, you have to. This is what you sign up for. So you have to do the R option. For 2010 students, you can choose to attempt these R options also for higher points. It's 110. Or leave it blank, don't touch it, and just do the normal one up to 100 points. this is reflected in the game system. So if you, for PS1, you are 2010 student, normal students, you want to do the bonus part, the R option, and you got it correct, then you get 110, about 10 points greater than everyone else who scored 100 in the normal version. Something like that. But you don't have to do this. Okay, I give you a rough idea. The R option requires requires understanding of data structures or algorithm beyond 2010. A self-research will be needed. Some pointers will be given, but not now. I want to let these R students think about it first. And my estimation is for PS1 R alone, probably you will need 10 hours if you haven't learned that thing before. So if I'm quite surprised some of you managed think that you solve it overnight on Sunday morning. I have received several emails from these people. I have tested it. So I'm not going to tell that people whether their solution is correct or not. If you think it's not, keep continuing, keep improving. Okay. So PS1 is about baby names. So let's. A story is about I got a lot of baby name suggestions, and I want to know how many names start with a certain prefix. Okay. So for example, look at the sample here. I have 4 distinct, always different. So one of you asked in the forum, it's always different. So there are 4 names: Robert, Jane, Maria, and Peter. 1 and 2 here refers to the gender suitability. Like 1 is for male, 2 is for female. I have a query. The query is in this form: starting value, ending value, and then the gender preference. I want to list down all names that start with PET or beyond, but does not include STE. So here, the answer is Robert and Peter. Because Robert is after PET but before STE. Peter is also in those 2 range, and both are male. So there are 2 names like that. This one, same query, PET, STE, but I'm looking for female. But Robert 1 and Peter 1 are both male names, so there is no such answer. You report 0. So something like that. So I give you a query. Tell me how many baby names in my list of up to 10,000 name suggestions. Tell me how many are satisfied to keep this query. Right. So there are 4 subtasks. Subtask 1, 25 points. This is the requirement. If you can solve this, you get 25. This will be discussed later today, if possible, or next week. Next tutorial is also possible. And then subtask 2, additional 25. Means that you need to solve subtask 1 first, and then your program can also satisfy the requirement of the second one. Then you get 25 plus 25 or 50. So it's all gradual. Subtask 1, 2, 3 are subset of one another. Subtask 4, subset of everything else. It's a bigger set of everything else. Something like that. Subtask 3 getting harder, and the additional 25 points. Subtask 4, additional 25 points to make it 100. One of you asked in the forum about something, and I say, yes, this is the wording of this subtask 4 is such a way that you have to write your own balanced analysis tree. You cannot use Java API, or you cannot use anything else. You have to use balanced analysis tree to solve this subtask to get 100. So listen to today's lecture carefully. That's the solution for this, right? For the R option, it's 110. I only changed one thing, literally. In the main problem, in the standard problem, I said, tell me how many names starts with this prefix. Starts with. But for the R options, I changed that to how many names, how many baby names contains certain substring. Simple, right? I only changed that too, those requirements. The solution is totally different. Really. Okay? I'm not going to give you spoiler. You can do some research on that by yourself. 2010 R student, there are 10 here, and There are 6 here and 10 outside this mode. Right? So take out your clickers and tell me about this. It's already open for 1.5 days for those who already noticed that. Where are you now? I have not even registered, means that I haven't even downloaded the question. I have downloaded, I have not read it. I have read it, but I'm confused what you are asking for. Or have you solved some of it? Are you waiting for these lectures to go on first and learn the knowledge before you start attempting PS1? Which one? Okay, it's almost 100 students here, so I will go faster now. Okay. Have read but confused. Yeah. Right. For this one person, can you quickly register now because you're in this room, right? Okay. Have solved subtask 4. Good. Right. No one has solved or think they have solved the R option. Okay. All right. So the game system is a combination between competition and collaboration. Do you realize that? So you have to compete against each other to get the better score. But then the wording of the requirement says you can collaborate. Do you realize that your main goal is actually to beat the game, not to beat each other? You can theoretically, all of you can get 15% if you work together, right? Do you realize that? This whole thing is created to make you talk against each other, with each other, discuss how to beat this system, how to beat this PS1 and up to PS8. The first few subtasks are easy, so there will be open discussions in tutorials and lab demos for the first few subtasks. The last one is going to be either difficult or tedious. So for subtask 4, I guess it's the second one is tedious because you have to write your own balanced BST. Right? But the R options is hard, very, very hard. So I encourage you to talk about it also, even if you don't have to attempt it. Okay? So this game system is to encourage discussion. That's why I want to see more discussions here. Last year, many students discussed, proposed test data to beat each other's code. So one proposed a very big test data, lots of names. Some other proposed another test cases and beat each other timings. If my test data, I got this answer and you got different answer, you know that either one of you is wrong, right? Or both of you are wrong. But if for this test data, 10 different students have confirmed I got the same answers, so most likely you are correct. Then you start comparing timings. Oh, mine ran in less than 1 second. Mine ran in 1 minute. So the other one should know that you are in danger because if your program runs too slow, there is a danger for time penalty there. Right? So you have to improve or change your data structure to make it faster. I encourage discussion like that. Okay? Next. So this is the main part of today. The first part, I will just quickly go through a revision of last week's material, binary search tree. And I give you a quick look of 3 files that I have uploaded, BST demo, est.java and BST for text.java. You may want to extend this to make it balanced. So I purposely don't show you the next one. At the end of these lectures, I will discuss a balanced tree called AVL tree or Adelson-Felski list. I will show you the code, but I'm not going to give you the Java file. If you want to use this for PS1, code it yourself. Okay? Right, and in the middle, I will highlight the main key points of today's lecture. What's the importance of being balanced, including in our daily life? Eat things in moderation. Right? And then, if you have my book, today's material will be on page 42, 43 on balanced BST. Okay, continue. That's right. This is the thing. the one I mentioned just now. Eat all foods in moderation. This is the key point that you have to take home today. Eat things in moderation. If you like ice cream, don't eat ice cream every day. If you like Coke or soda drink, don't do that every day. If you like coffee like this, only use it when you have to maintain yourself to be awake for the next 2 hours. Something like that. Don't overuse. Don't overdrink. So, okay. We will revise BST topics. A quick review. So what's BST? BST is a binary search tree. You have non-binary search. You add 3 on top of it. Right? So binary search tree, for every vertex, it has 2 children, left and right, and 1 parent. It has a value. We call it key or dot value or dot key or dot data, something like that. But here I just use dot key. And every node, every vertex, every circle in that tree has property that everything on my left, including all my left children, must be smaller than me. Everything on my right children must be greater than me. Greater in terms of value. So let's take a look. If I'm 41, everything on my left must be less than 41. 20, 11, 29, all less than 41. Everything on my right, 65, 50, 91 are greater. This must be applicable for every node. If that's true, then I am a BST. So, is this a BST? I use clickers to verify your understanding. I hope many of us got correct answers. Otherwise, there is going to be a slow revision happening. Try to get as many correct answers as possible for the next few slides so that I can continue comfortably. Is this a binary search tree? Yes or no? Or number 3. Okay, 32. Let's see. Yes. Right. So 20. This is L. So 11 is on the left, so it's correct. 20, 29, this is R. So 29 and 26 are both right subtree of 20. Correct. 29, 26, this is the left. Correct. So it is a binary search tree. Next. Is this a binary search tree? Okay, 31, 32, let's see. No, correct. Because this 42, although it looks correct and it looks like on the right side, but 42 is connected to 29 and connected to 20. So it's 20, 11, 29, 42 are all left subtree of 37. And that's wrong because 42 must be on the right of 37. So can you see that if you draw the BST wrongly, you can confuse yourself. Imagine what happens if you do that for our exams. I ask you to draw a BST and you draw it like this. Most likely, if I'm not careful, I will mark you wrongly. Although your intention is to draw a BST, but you draw it in a confusing manner. Then the markers, the grader, if they don't do it carefully, they will mark it wrongly. Okay? So don't do that. This bad illustration is to show you that if you draw BST in funny way, it's harder for you to understand it. Next, insertion. I want to insert 33, the new value 33, into this BST. Where will it be inserted? Where will it be inserted? Recall, insertion will start from root, find the correct insertion point. It will always be a leaf, a new leaf, and once it is inserted, it will not violate by a BST property. There is only one possible position for every insertion. The answer is, yep, correct, on the right of 29. Good. Continue. Successor is a concept that we have learned last week. If you have a node, you want to find your successor, there are two conditions. If you have your right subtree, find the minimum of your your right subtree. If you don't have right subtree, keep moving up until you make if you make a right turn, if viewed from bottom. As soon as you make the first turn to the right, that's the answer. Okay, let's see. Yep, correct. 38. Those who say 65, you are deceived. Because 65 is right subtree, but then you have to go left, find the minimum of this right subtree, which is 38. So 38. For those here, 6 of you, be careful. So, last week I have shown you all pseudocodes. If you want to make it work, you have to convert those into code. Right? So this time I will show you how to do it. And see that I already have everything, but I'm not going to give you this AVL.java. I will give you something else. Okay? So let me open BSD.java. I will enlarge the font size. Yeah, something like that. Okay, should be large enough, right, for those at the back. Okay, so I have this is written in object-oriented fashion. I should start with BSD for text first. So BSD for text. So BSD for text is a simple class. It contains several important values: key, parent, left, right, and height. Height is a new thing that will be used later for AVL. So for now, it's not used. I have key, the value of this vertex, parent, who is my parent, who is my left, who is my right. Initially, everything is null. Okay, and I have reference to, this is a recursive reference. I have reference to my parent, to my left, and to my right. So every node has 3 other pointers. Right? Then it has its own value. For now, it's an integer. Okay, so this is BSD vertex. And then class BSD is this. I have a special vertex called root, so I remember only the root. So I will always start my searching, my insertion, my deletion, always the reference point will be root. So this is, I will only show some implementations. You can take a look at everything else by yourself. Just like a look at search. In my lectures, I mentioned pseudocode, but here is how to write it in Java code. You need to use like protected BSD vertex search. This is the current node. This is the node that you are looking for. If the current node is null, you say not found. It's null, return null. If t.key is v, you found it, you return t. If it's smaller, you recursively go to your right, looking for the same fee. If it's larger, look for your left, it's the same fee. Okay. How about insertion? Same thing. If you hit an empty tree, means that you hit the correct insertion point. What do? You create a new node there. Right? And then if it's smaller, go to right, larger, go to left. Once you have inserted the new node, you also need to update your parent pointers. Otherwise, the linkage is not correct. I have shown you why we need the second line last time. Okay. And so on for the rest. Okay, something like this. Okay. Once you have written a class like this, then you can use it. So look at BSD demo.java. So once you have a BSD.java and you are confirmed sure that this BSD.java works correctly, you can use it for other projects. So you can create BSD T equals to new BSD. I'm going to read in several numbers, and these numbers I will insert one by one into a tree. I will insert one. So this is my test data, BSD input. I will insert 15, 32, 106, blah, blah, blah. This is the same number, almost the same number. I changed 100 to something else, as in our lecture note. right? Then I show you, I call t.search, and so on, and then call in-order traversal and so on. Then if everything works correctly, you should see something like this. Right. Search of 71, yes, I found 71. Search of 7, I found it 7. Search of 22, I don't find it, -1. This example is, if I'm not mistaken, I changed 100 to something else, but the rest are the same. So this is the same as last week's lecture notes. Right, so you can play around with this and test it yourself. Right. But what happens if you just use bst.java in PS1? Alright, what's the worst case of binary search tree operations? The worst case of binary search tree operations. H is the height of the tree. I can give you name suggestions where all 10,000 names start from A to Z or Z to A, whatever. It's all going to be a linked list, right? So Andy, Bob, Cindy, Debbie, whatever, A, B, C, D, and the Z like that. Then your BST will be a linked list actually. If I ask for a certain name, you will search on this linked list. Insert a new name, you will again search on this linked list. So that's going to be very slow. So you have to improve this BST.java into a balanced BST. So that's what we are going to learn today. Right? So first you have to understand how BST works and how it's implemented, but then you have to realize that it's not enough. You have to have the true advantage of BST operations, the log n operations. You have to make sure that the tree is always balanced. So that's the key idea of today's lecture. Okay. Some more quick review. If this is a tree, a BST, the very first node, we call it root. Those that are has no more children, we call them leaf. The rest we call them internal nodes. Root is also internal nodes, but it's also a special node called root. And today we are going to learn a new property. So last week we have learned left, right, parent, and the key. Four of them. I want to add one more, the height. So every node remembers one more attribute, which is the height of a tree rooted at that position. Okay. So we define it as this. The height of the tree is the number of edges on the path from this vertex to the deepest possible leaf. Okay. These values can be computed recursively. Initially, if I'm an empty tree, it's -1. Other than that, it's the maximum of left and right, the maximum of the height of the left and the right subtree plus 1 for every other cases. The height of the overall BST is the root.height. We will take a look at the same picture and look at the leaves first. Look at the leaves. The leaves have left and right subtree blank, right? According to this definition, if I have a blank tree, empty tree, the height of it is -1. So left subtree is -1, right subtree is -1. So everything like that. See, if I'm internal node without left children, this will be a blank tree, right? -1. See that all here are -1. Now, what is the height of the leaves? Will be maximum of left and right subtree, the height of left and right subtree, which is maximum of -1 and -1, which is -1, right? Plus 1 becomes 0. So look at this. So all the leaves have height 0 because -1 and -1, the maximum of those is -1. Plus 1, it will be 0. So all the leaves will have height 0. Next, how about the one above the leaf? Look at this. Or look at 29 first. For 29, my left subtree is -1. My right subtree is 0. The maximum among the two is the right, 0. 0 plus 1 is 1. So 29 have value 1. How about this? 91, left and right are both 0, 0. So the maximum of those is still 0. Plus 1 is 1. So 29 and 91 both have height 1. Got it? I continue. 20. I have 0 and 1. The maximum is 1, right? So 1 plus 1. So 20 will be 2. Same thing here. 0, 1. This will be 2. 2, 2. And then finally the root is maximum of 2, 2, which is 2, plus 1 is 3. So the height of this tree is, the height of this BST will be the height of stored in the root, which is 3. You can verify that from the root, the number of edges to the deepest leaf is 3. Look at this. 1, 2, 3. Or you can go 41, 65, 91, 72, 3. Or you can go 41, 20, 29, 32, also 3. So from 41 to the deepest possible leaves, there can be more than one. You need 3 edges. So the height of the root will be 3. Let's take a look at 20, for example. 20, if you go left, it's only 1 step. But if you go right, it's 2 steps. So the height of this node 20 will be 2. So for now, let's concentrate on this concept. I have a new attribute called height. I will store this attribute height in every node in my BST. I want to know from this node to the deepest possible leaves what is the number of edges taken. Okay. So test it. I want to test this on this funny looking diagram again. What's the height of this tree? Means that what's the longest possible number of edges taken from this root 41 to the deepest possible leaf? What's the height of this tree? There are 2 ways to do it. You can start from bottom up like that. From all the leaves is all 0, move up until the root. Or you can start from the root and trace what is the longest possible edges. Either one is fine. And the second one is faster. One more. Okay, never mind. 29, let's say. 5. Correct. You can. I say the second approach will be faster because you just need to count the number of edges from root to the deepest possible leaf. So here you look to your left, it's only 2. Here to the extreme right, it's only 2. So at this point you need to go left, right? So 41, 65. 50, 91, 3 already, right? 3. If you go left, it's 4. But if you go right, you can do 2 more. So 5. Either 91, 99, 32 or 99, 29. Both will give you the path length of 5 edges. So 5. The height of this tree is 5. Right. So look at the last slide when I said that after talking for 1 hour, 2 hours, 1.5 hours about BST, I end up saying that the worst case of BST is ON. Because what? The height of the tree can be a linked list. And a linked list means that you have a root and you always go to the right, or root always go to the left, and the performance becomes ON. But for many other cases, it's not. It depends on the height of the tree. OH. So in the last slide we have discussed height of a tree. So you can see that if this H is not controlled, it can be as big as N, and that is bad. But in the next few minutes we are going to see how to make sure H, the height of the tree, will never go more than log 2 of N, logarithmic of N. There is a way to do it. So out of these operations, only in-order traversal is not affected by H, it's ON. In-order traversal is given a BST. When you run in-order traversals, it will produce the sorted output of the content of the BST. But the rest mostly depends on H. Alright, so let's look at the importance of having a balanced tree. So see that most operations have OH, right? And let's establish the lower bound. How low can the height of a tree of n vertices can be? I have a tree with n vertices. How low the tree can be? The tree can be very low in terms of height if I have it very balanced like this. Every node has two subtrees. Every node has two subtrees, and I will do it level by level, right? So that if I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. If I have 15 nodes, I will place them like this. I place them like this so that I only use height equals to 3, right? 41, 20, 29, 22, or some other combinations. I only need 3 steps from the root to any possible deepest leaf. And eventually here all the leaves have the same depth, 3, h equals to 3. Do you realize that 15 and 3 is related by logarithmic? 15, log 2 of 15, I round it up, is actually log 2 of 16 is 4. 4 minus 1 is 3. So one more layer, for example, if you add one more layer, then you can have a total of 31 vertices. And the minimum height of your tree will be 4. So imagine that for 5 you draw two more children, for 13 you draw 2 more children, and so on. The total that you have is 31. And the height of those compact tree is a balanced tree is 4. Right? But this is the minimum that we can do. We have to perfectly balance left, right, left, right, left, right. So this is the lower bound. But what's the upper bound? Before that, some numbers first. This is height 0, right? If I only have the root, it's height 0. If I have the children of the root is height 1, and so on. Okay. So there are how many elements in this level 0? Only one element, the root itself. How many elements in level 1? 2. Left children and right children of the root. How many elements in level 2? 4. Left and right children of this guy, left and right children of this node, so there are 4. See that every level you duplicate the number, you twice larger. So 1, 2, 4, 8, and so on. Okay. And the last will be 2 to the power h, the last entry. Okay. So okay. If we arrange the nodes in a balanced fashion like this, then we have one node in first level, level 0, 2 nodes in level 1, 4 nodes in level 2, and so on. We need to establish that this is greater or equal to n, so that we can store all those n nodes. This can be rewritten as a sum of geometric progression into 2 to the power h plus 1. Right? Can you see that? 1 plus 2 plus 4 plus 8, you sum them together, is 15, right? It's 1 less of 16, 1/6. The next layer, if you draw another 2 for each leaf here, is 31. 31 is 1 less of 32. The next layer will be 63. 63 is 1 less of 64. You can generalize it using sum of geometric progression. N will be less than 2 to the power h plus 1. Actually 1 less than this. You put a log on the two sides. Log 2 of n less than log 2 of 2 power h plus 1. You can put down the h plus 1 down, right? Becomes h plus 1 times log 2 of 2. Log 2 of 2 is just 1. Cancel this out. So h will be log 2n minus 1. Hopefully this is not too scary. Okay. Repeat again. 1 plus 2 plus 4 blah 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 is the number of nodes if I arrange the nodes in a balanced fashion like this. Every node has 2 children, every node has 2 children, like that. Means that in the first layers I have 1, second layer, first layer is layer 0 is 1, layer 1 is 2, layer 3 is layer 2 is 4, layer 3 is 8, and so on. Okay, 1 plus 2 plus 4 plus blah blah blah, blah until the last layer must be 2 to the power h, right? Sum of these must be greater or equals to n so that I can accommodate all those n nodes in this balance tree. Right? This 1 plus 2 plus 4 blah 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 can be simplified using sum of geometric progression into 2 to the power h plus 1. Add one more layer. 2 power h plus 1. Then I'm going to use some logarithmic manipulation. I put log on the two sides, log 2 on my left and log 2 on my right. So previously is n less than 2 to the power h plus 1. I put log 2 on both sides, I get this. Now look at this. Log 2 of 2 to the power h plus 1, the power h plus 1 can go down. So it becomes h plus 1 times log 2 of 2. Log 2 of 2 is 1. Right? It just cancel each other. Okay? 1. So it means that log 2 of n less than h plus 1. In other words, h will be greater than log 2n minus 1. So this is the lower bound that we can do, the best that we can do. The height of our BST will be at least log 2 of n minus 1. At least. It will be greater than that, but at least this. It cannot go lower than that. Okay? But how about the upper bound? We have seen this picture many times last week. If I give you if I insert nodes to a BST in sorted fashion, I ask you to insert 41 first to a blank BST, and then 65, 91, 93, 95, 96, 97, in that fashion, then the resulting BST will be a linked list. And the height of this will be n minus 1 actually. Right? The number of, so 1, 2, 3, 4, 5, 6, 7. There are 7 nodes. How many edges from 41 to the deepest leaf? 1h, 2h, 3h, 4h, 5h, 6h, n minus 1. But it's correct, right? H will be less than n. H can be up to n minus 1. Right? So can you see that we have a range now? You combine the bound. The height of the BST can be as low as log 2n and can be as high as n minus 1 or n. And last week I told you that the range between log and n is very huge. So look at this again. Log and n in picture. If I have n equals to 500, then log 2 of n is just about 9. It's just 9. 2 to the power of 9 is 512. If I have n equals to 1000, which is double of 500, log 2 of n is just 10. Can you notice the difference between this and this? This is really drawn to scale. It's really drawn to scale. So if you just stop at your 1020 last semester's knowledge, then your program can be very slow. But once you can make sure that all basic data structure operation runs in logarithmic time, you can make it much faster. Okay. So there is a gap, right? The height of the tree can be between log and n. It's a huge gap that you can play with. If you end up having a balanced tree, your performance is like this. If your tree is unbalanced, your performance is very, very, very slow. Some of you asked when I released PS1, how much time limit do you give for when testing our code? I said a few seconds. How many few seconds? I said I don't care, because if you run the n square or n operations, versus if you use this one, the gap will be very noticeable. One of them will run in less than 1 second, the other can run in 1 minute. So few seconds can differentiate the two. So that's why I say it doesn't really matter. And a few seconds doesn't really matter. Because once you use the correct algorithm, the correct data structure, the gap will be there. Will be very noticeable. Okay. So what we want to establish today is how can we get this log n performance? How can we bound the height of our tree to be at most log n? So look at the wording of O. In our asymptotic notation, O bracket log n is not really the you can say that h equals to a constant times log n, right? We are going to play with that constant. We know that the lower bound is log 2 of n, precisely 1 times log 2 of n. But our tree will also be classified as a balanced tree if we can play around with the constant c times log n, so that it's still true, right? That our tree is a constant factor of log n. So it's still bounded by the height of log n. And in this case, for FVL tree, that constant factor is just 2 log n. We will see in the next few slides. Right? So this is the perfectly balanced tree, which is very hard to achieve. So a person called Ederson, Felsky, and Landis in 1960s, many moons ago, 50 years plus something ago, they created this kind of strategy. If getting perfectly balanced tree is very hard, what if I relax the condition a bit so that I'm okay if they are differ by the height of the tree differ by a bit? So I'll control that so that the performance is guaranteed to be still log n. Right? So they define something like this. They define the property of a good, or they define a good property of a tree, and they will maintain this property all the time, at all times, especially during insertion and deletion. Make sure this property always true. If it's no longer true, fix it. Make it always true. Then if this is maintained, then the tree can have a log n performance. So I will go through a few slides of this and we'll take a break. What is the concept proposed by this person, Ederson, Felsky, and Landis? If I'm not mistaken, both are Russian. Let me check my wording here. Yes, Soviet, correct. Yeah, Russian. Ederson, Felsky, and Landis are all Russian. 1962, which is 50 years ago. You were not yet born. Same thing with me. I was not yet in the world. But they already invented this data structures. Right? The loss of recursion in the next few slides, in the next 1 hour, so hang on. Okay. Right, so this FVL tree uses the concept that we learned just now, the height of a tree. Right? And now they want to maintain the property of height at all times. So every time you do insertion or you delete things, they will always want x dot height, where x is the node vertex of a BST. The content of x dot height is always true. Right. So during insertion and deletion, we also update height if necessary. So FVL trees do the first modification here. So during insertion, you go left and right as per normal. At the very end, you have this statement. This is what? This is the checking of updating the height of a BST. You will update the height of the BST during insertion. Same thing with deletion, but not shown. Okay? So this is the example. So suppose you already have this BST and have already computed the height of every node. So 41 have height 2, right? Correct. 2 steps to deepest leaf. 20 has height 1 step to the deepest leaf. Same thing with 65. And all the leaves, 11, 29, 50, currently have height 0. At this point, every numbers are correct. Every number h equal to something, that's always correct for this case. Now I want to insert something. I insert 27. When I insert 27, I have to compare with root. Go left, right, because it's smaller than 41. Go right because it's greater than 20. Go left because it's less than 29. So I'm going to insert 27 here. When I insert 27, I know that the height of 27 must be 0 because this is a new leaf, right? But what happened with 29, 20, and 41? All have wrong numbers, right? This is 0, 1, 2. All of them are wrong now because of new insertion of 27. Don't worry. When we go back, see that the recursion works like this. You insert left, right. When you want to go back, you update the height and then you go back. Okay. So when you want to go back, see that after you insert, you want to go back, right? So from 27, when you go back to 29, you update one statement. Compare 0 with -1. Oh, the maximum is 0 plus 1. So I am now updating my height to 1. Then I go back to 20. 0 and 1, the maximum is 1. 1 plus 1 is 2. So I update myself to 2. And so on with this. So look at the animation. I insert. This is the path that I need to go through. I create 27 on my left. I immediately know that the height of this 27 must be 0. Then when I go back, see that 29, 20, 41 all have plus 1 there. Okay. Not every insertion changes the value of h. I repeat again, not every insertion changes the value of h. For example, what if now I insert 31? See, 41, 20, 29, 31. 31 we have height 0, right? But do I need to change 29, 20, 41? No. But will my code do that correctly? Yes. Because when I go back, suppose I have 31 here. 27 and 31 will be 0, 0. The height of 29 will be 1, right? Correct. So no change. So remember, again, I repeat, insertion may change the value of height at certain nodes. And that certain nodes will be the path from root to insertion point. You only need to check that those paths. The rest will not be affected. But not every time. Not every time. Only in this case, for example, in this case, it affects the path from insertion point up to the root. Okay. Okay. One slide before, one slide, and then two clicker slide, and then you will stop. Right. So Ederson-Velsky, they add this they add this technique. I want to maintain the value of height for every subtree at every time during insertion and deletion. I only show insertion here. Right. The modification is very simple. After insertion is done, when you want to backtrack, you check again the value of height, update if needed. That's the first change. The second change is they say that I'm okay if a vertex X is declared to be balanced if the difference between height of the left and right subtree is less equal to 1. The absolute difference. So it can be 0, minus 1, or plus 1. The difference is just 1, less equal to 1. If it's the difference between left subtree, the height of left subtree and the height of right subtree equals to 0, means that they are balanced. Left and right have the same height. But if they are different by 1, then I'm also okay with that. I'm also okay with that. And then if I maintain this property for every node in my tree, then I say my tree, my BST, is also height balanced. So every node, I allow them to be imbalanced by plus minus 1. If I do that for every node, my tree is said to be balanced. Okay. So this is a pictorial diagram. If I am a tree rooted at X, I have a left subtree. The height of my left subtree is K. My right subtree can only be K minus 1, or also K, or K plus 1. Cannot be K plus 2. Cannot be K plus 5. Cannot. If my left subtree is K, my right subtree can only be K minus 1, so that the difference between left and right is plus 1. Or the right subtree is K also, so K minus K is 0. Or the right subtree is K plus 1, so K minus K plus 1 is minus 1. Other than that, I have to fix something. Okay, so we stop here, but just to check, is this tree considered height balanced or not? How to check whether at every node the difference between the height of left and right is always at maximum 1, absolute difference. True or not true? This is not perfectly balanced, right? Because see that 20 has 11 on the left, but 29, 32 on the right. So they are not perfectly balanced. But is it considered height balance according to Ederson-Velsky and Landis? Yes, they are. Because you can try every node. They are not differ by plus minus 1. One more slide. This one, is this height balance or not? should be easy to spot, because previously this is almost similar to previous slide, and you can notice something is clearly not balanced starting from the root. Should be no, correct, yes. Because at the root, look at the left side of the root, it's only 2, right? But at the right side, 1, 2, 3, 4. 2 minus 4 is minus 2. Minus 2 is not considered balanced by Adelsson-Felski. We stop here, we come back at 11.5. 11.5, isn't that so? So if you have, if you are not clear with the concept of height, balance criteria, ask me. Yeah.
This is supposed to update the whole tree on the height, is it? Shouldn't this be root if that's the case and not x?
Test. Okay, we will continue. I will need your attention because the next few slides is proof heavy, and last year this is the several slides that almost always asked by people after lecture. I will try my best to explain as clear as I can. If you still have further queries after this, fine. Okay. Right. So 5 minutes ago we stopped at saying that Anderson-Felsky maintained two things. Anderson-Felsky proposed two things. During every insertion and deletion, you always maintain the theory of height of every node. You can do that during insertion by, when recursion unwinds, you always update the height of the tree affected nodes. Second, they say that I'm okay by having a slightly unbalanced tree, but that unbalancedness must be plus minus 1. And they say if this is observed for every tree in the node, every node in the tree, my tree will be balanced. Right? So then they claim that a height balanced tree with n vertices, the height of such tree is less than 2 log n. The magic number is 2 times log n, 2 times. If this is true, then the height of the tree will be log n, right? Because you can drop the constant 2. So the performance of your BST operation will be log n. So then, if I just say this, many people will be confused. Why? How come this is true? So I'll give you a proof. Simple. Hopefully, it's quite simple. This proof looks like this. Let nh subscript h be the minimum number of vertices in a height balanced tree of height h. And I have a tree, the tree of height h. The number of nodes in this tree of height h, the minimum such node will be nh. In the next few slides, I will establish that nh is greater or equal to 2 to the power of h over 2. In the next slide. Okay? Look at this. If I have this equation, if I put log on both sides, then h over 2 can go down, right? Log 2 of 2 will be 1 again. So h will be 2 times log n. 2 times log nh. So if I can establish this condition, h will be 2 log, less than 2 log n. So how to establish this condition? Next slide. Right. Okay, hopefully this is clear enough. If I have a BST that you can draw it like this, if I have a root node here, do you realize that according to BST FVL property, my left and my right can only differ by at most 1. Alright? NH is defined by the minimum number of vertices. So if I have left subtree have height h minus 1, the right subtree also have h minus 1, that's not the minimum. Because what? FVL says I can reduce either one of the subtree by one more level, so that they are slightly unbalanced by plus minus 1, and it still satisfies FBL property. So in this case, I put my right subtree to be of height h minus 2, slightly less. Okay. I can reorder this from left, make the left one h minus 2, make the right one h minus 1, fine. But here, to make it simple, I only take the left one to be h minus 1, the right one to be h minus 2. Okay. Okay, why there is a minus 1 and minus 2 there? Because I'm the root. I take out one level already. So if I have a left subtree, the height of this must be at most h minus 1. Right? There is a minus 1 there. And why this is minus 2? Again, because I have used one level for my root, and then I'm allowed to remove one level at the bottom here. I'm allowed to remove this one, so that they are unbalanced, but only by h minus 1 minus h minus 2, which is plus 1. Right? They are only unbalanced by plus 1. And this is the minimum possible configuration that I can get. Then I can recursively apply the same condition. If I have a tree of height h minus 1, the number of nodes must be n h minus 1. The minimum number of nodes in this subtree. Same thing. If I have a tree of height h minus 2, the minimum number of nodes will be greater or equal to n h minus 2. So, is it true that nh must be greater or equal to 1? Where does it come from? The root itself, right? I need one node for the root. And the minimum number of nodes on my left subtree, nh minus 1, this guy, and plus number of nodes on my right subtree, nh minus 2. Up to here, understand or not? Okay. Okay. Now the magic transformation. Ding. Like this. Why suddenly 1 plus nh minus 1 becomes another nh minus 2? Okay. See that the only changes between these two lines is 1 plus nh minus 1 becomes another nh minus 2, so we have 2 nh minus 2. Why does it happen? Because of the equation is greater equal. Right, look at this. nh minus 1 is definitely bigger than this, right? Because it's slightly one level higher. Definitely bigger. Definitely bigger by how much? At least one more node. Right? So, at least by one more node, right? So, this thing can be replaced by nh minus 1 without changing this whole equation. Got it? I repeat. nh minus 1, you can suppose you can have a tree that ends here, but have one node extended in my left side, so that the height becomes h minus 1. This one is the one extra node that you can imagine this triangle as this one plus one extra node. Then it becomes h minus 1. The height will be h minus 1 instead of h minus 2. This one node, I replace it with the root. So, this guy is this one plus root. Roughly the same, right? So I can substitute, not like roughly the same, it's the same. So, I can change 1 plus nh minus 1 into another nh minus 2. So, it's 2 nh minus 2. Up to here, understand? Alright. Now, here comes the recursive thinking. If I have nh minus 2, is it true that I have nh minus 2 is greater or equal to 2 nh minus 4? And if I have nh minus 4 greater or equal to 2 nh minus 6, and so on. So I can do that. Okay? This nh minus 2 is 2 times nh minus 4. 2 times 2 nh minus 4 is 4 nh minus 4. And then nh minus 4 equals to 2 times nh minus 6. Becomes 8 times nh minus 6. And so on and so on and so on and so on until sooner or later nh minus something will be the base case. It's when n0, right? N0 is what? What is the minimum possible node if I have only n h equals to 0? Means the height of the tree is 0. Means that I only have the root itself. The base case, nh cannot be lower than n0, which is 1, the root itself. Up to here, okay? All right. Now, this whole thing, see that I reduce h by 2. I start with h, become h minus 2, become h minus 4, h minus 6, and so on. To make the proof simpler, I assume h starts with even number. For example, h equals to 10, for example. 10 go to 8, 8 go to 6, blah, 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 until it goes to 0. After 5 steps, every even numbers will become 0. After h over 2 steps, any even number of h will go to 0. Right? So, this whole process is repeated h over 2 times. So, I can say that, see that the pattern is always increasing the power, the constant by 2, and decreasing the subscript by 2 until it becomes n0. This increase will stop at 2 to the power of h over 2. Because you can only do this h over 2 times, right? So at the very lowest entry, the lowest entry here will be nh, here the lowest entry here will be nh greater or equal to 2 to the power of h over 2 times n0. And we have seen that n0 is 1. So nh is greater or equal to 2 to the power of h over 2. And we have seen earlier that I can put log on the two sides, h will be less equal to 2 log n. So, by this, Adelson and Felsky claim that if you can maintain that I am okay if my tree is slightly unbalanced, but I will make sure every of them, every node will only be unbalanced by plus minus 1. If I can do that for every node in my FEL tree, which is a BST, my FEL tree will be balanced. It will be at most, the height of my FEL tree will be at most 2 log n or log n. Right? So, the final question then becomes how they can always maintain height balance for every node. Okay. So, if I have a node, either my left is k, the height k, or my right is k minus 1, or my right is k, or my right is k plus 1. Right? How to always maintain this? Say that I'm going to give you a case again, insertion, that will cause a previously balanced tree to become unbalanced later. So this is the slide. This is the tree that I have shown in the MCQ slide earlier. You have all said, almost everyone say that this is balanced. Initially balanced, right? You can verify it's initially balanced. Plus minus 1 for 20 is minus 1, for 61 is minus 1, 41 is 0, 29 is minus 1, right? 91 is also 91 is 0, balanced, right? 29 is minus 1, something like that. But nothing is plus 2 or minus 2 or greater than that. So this is a initially balanced FEL tree. Now I want to insert 37. Where 37 will be inserted? It will be at the right subtree of 37. See that once I do this, 29 is no longer balanced. 29 has 0 left subtree, nothing on the left, and has 2 on the right. So 0 minus 2 is minus 2. It violates the balance property of BST. For 32 is still fine because 0 minus 1 is minus 1. Fine, still fine. Same thing happening with 20. I have 1 here on my left, I have 3 on my right. 1 minus 3 is minus 2. So see the insertion of 37 causes the initially balanced tree into no longer balanced. So something must be done. We need to rebalance. And this is the confusing part of FEL tree. But how? They means Adelson Felsky invented an operation called rotation. Rotation. And rotation has 2 similar actions, right rotation and left rotation. So let's concentrate on the structure on your left. I have PQ, Q have left subtree P and right subtree C. P has left subtree A, right subtree B. If I say I want to right rotate on Q, you can see that it is really like a right rotation where P will move up, Q will move down right. Okay, so look at it. P will move up, Q will move down and right, okay. And then Q is still connected to C, same, okay. P is still connected to A, same. But there is some magic changes here. B, who is previously the right children of P, becomes the left children of Q. Okay, the question for many of you is why? Okay, look at this. When I do right rotate on Q, I rotate on Q, then P will have right children Q. Previously, P has B as its right children. And we know that a node can only have one other node as right children. So no one can take care of B if I rotate right on Q, because P will have to take Q as its right children. So B can no longer be the right children of P. So someone else must take over, otherwise P is dropped. B is gone. B is gone, sorry. So B must be taken care of by someone else. And the only possible node that can do that is Q now. Because look at this. When when I do right rotate on Q, Q will still have right children C, but then its left children will be gone, will be empty, right? It will be empty because previously it's P, but after doing right rotation, it becomes empty. And if you shift B to left children of Q, the ST property will not be violated. It will be true. Okay? So, that is right rotate on Q. If you do left rotate on P, you will get the same structure. So you can keep rotating left, right, left, right, left, right, and you get the same structure back and forth. This concept requires practice to understand. So during tutorials, we will give you more exercise on this. Okay? So this is the first exposure on rotation. And if you want to do subtask 4, you have to implement this. Oh yeah, by the way, during the break, one of you asked, can we use your bxt.java, the one that you uploaded in lecture notes? Can, because that one is unbalanced. I purposely do that. That one is unbalanced. So if you copy that, confirm you will not pass subtask 4, because you can assume that I give you a baby names, 10,000 of them, all sorted. Either sorted descending or sorted ascending or slightly sorted, something like that. You can't guess. And that's guarantee to a weak implementation to run slowly. Right? So you need to balance them. How? You really need to implement this. Okay? Right. So I'm going to give you a pseudo code on how to do rotation. I will only highlight rotate left, because rotate right is the same. It's the mirror copy of each other. Okay. Now, this slide can be confusing without animation. So I will highlight the animation one by one. All right. Yeah, what am I trying to say here? Okay. Rotate left. Okay, I'm going to do rotate left of P. So look at this diagram. Okay, rotate left of P. So I have a tree structure that behave like this. P, I have left subtree A, and notice that A, B, and C can be a null, can be an empty subtree. Right? For the sake of completeness, I will just denote them as A, B, and C. P has A as left subtree. P has Q as its right subtree. Q has B and C as left and right subtree. The green arrow are the parent pointers. You will need these parent pointers. Right? So now I want to rotate left on P. So I pass P here as a parameter of this function rotate left. So T here, this parameter, points to this guy, P. Right? Then my first line is I want to remember the right subtree of T. Which is Q, right? Yeah. So here I say W equals to T dot right. So W will be this Q. Right? Next line. W parent equals to T parent. What's that? Someone's iPhone's alarm. Yeah. There's iPhone, definitely. Okay. Okay, back to this. Okay, look at this arrow, this one. So rotate left will only manipulate some pointers. This is the first pointer that we're going to manipulate. W.parent equals to T.parent. So previously W.parent is P, right? But P is somehow connected to some parents of P, one parent of P. I will say W.parent, now you connected to T.parent. So I'm from P.parent, I ask Q to point to the same parent, so that this subtree is not detached from the main tree. Next line, T.parent equals to W. See, look at the next animation. T.parent equals to W. Previously, T.parent is a node that is a parent of P, right? But now after left rotation, this must be this. So I have to update this. T.parent must be Q, and must be W, which is Q. Next. Look at the animation. Okay. T.right equals to W.left. Okay. W.left, Q.left is B, right? Q.left is B. Now I want to pass over that job to P. So I say P or T.right will point to B. One more. If W.left, which is B, is not null, I will say W.left.parent point to T, this one. Okay. Why do I need this check? Because B can be an empty tree. If this is an empty tree, you call empty.parent crash. So you will need this line to check. And then finally you delete, you change this. Okay. W.left equals to T. W.left, which is B, now it must point to T, which is P. Yeah. Update the height, and then update the of T and then W, and then stop and then return. See that what I have done here is just manipulating 4 pointers. I only changed 4 arrows involving left, right, and parent. By doing so, I can rotate this structure to this structure and preserving all BST properties. Since I only manipulate 4 lines, 4 constant lines, it's considered O1. O4, you can say O4, but it's O1. Right. Rotate right is the mirrored version of this. This takes time to understand again, yeah. You will need some practice to understand. The next concept is balance factor. Right? Balance factor is nothing new. It's the difference between left and right subtree. But there is no, I don't use the absolute value because the plus and minus will mean something. So balance factor is the height of the left minus the height of the right. And once you do insertion, you check the balance factor from the insertion point upwards to the root. Once we hit a +2 or -2, we do something with it. So we insert, just now we insert 37, right? What's the balance factor of 37? Empty minus empty, 0. What's the balance factor of 32? Empty minus 1, minus 1. What's the balance factor of 29? Empty minus 2, minus 2. Right? So there is a -2 here. As soon as you hit a -2 or a +2, you will need a rebalancing action. And how do we rebalance? There are 4 cases. Oh, getting complicated. Yes, it's getting complicated. Right. So, getting complicated. Now look at the structure of your tree. If you have a structure that like this, I have a value x, and x, the balance factor of x is +2, and my left is +1. I do right rotate. Right rotate should be this one. 2. Here, sorry. Yeah, this one. I am x. Look there. This line. You can draw an arrow to this case. Okay. Let me just throw it for you. Okay. If my x is 5, this is a sample. If I have a balance factor of x is plus 2, and then my left is plus 1, see, this is my left. This is my left. Then I do right rotate on x. I right rotate on 5. I will get a balanced tree like this. 5 go down, 4 go up, 3 go up, and C becomes the left subtree of 5. Then I have a balanced structure. But if I have a condition where x is plus 2, x is plus 2, and my left happens to be minus 1, if you just do right rotate, you will mirror it to this condition without fixing anything. So if you just right rotate here, if you just right rotate on 5, where your left subtree is minus 1, you will mirror it to this, which doesn't help, because it's also unbalanced. So if you have this situation where x is plus 2 and left of x is minus 1, you do left rotate on x first. You do left rotate on x left first. So you do left rotate on 3. When you do left rotate on 3, do you realize that you make it to this one? Then once you have this, you can use the previous case to make it this. Okay. And the mirror version is for the same. You have minus 2, minus 1, just do left rotate. You have minus 2 and plus 1, right rotate first on x right, and then left rotate. A bit confusing maybe. Let's see this in example. Right? This is 0, this is minus 1, this is minus 2. When you go up and fixing the balance factor property, you will hit, once you hit a plus 2 or minus 2, there is a sign for you to do something. Here is minus 2. So this is your x. If this is minus 2, you need to check your right subtree. Your right because if it's minus 2, you need to rotate left, right? But before you rotate left, you check your right subtree. It's minus 1 also. Since it's minus 1, it's an easy case. By just doing left rotate on 29, you will have this. See? You left rotate on 29, you push 29 downwards, you push 29 downwards, you push 32 upwards, 37 upwards, and it becomes balanced again. For insertion, you just need one one action for fixing balance property. For deletion, it can be from that deletion point outwards to the root. I don't show deletion, but that's the main idea. Okay, so for insertion, the summary of ideas is this: you insert as per normal, as in normal BST, and then walk up back from the insertion point to the root. You check the balance factor. How to check balance factor? You first need to update the height of left and right subtree, and then update the balance factor of yourself. As soon as you hit plus 2 or minus 2, do some action. There are 4 possible cases. Can be just left rotate, or left right, or right left. Something like that. There are 4 cases. Deletion is a little bit more complicated. I will skip that for 2010. I will not use it in PS1, because if you see, PS1 involves add suggestion or insertion, and then query or search. Do I have delete suggestion? No, maybe next year. But if I have delete suggestion, then I have to explain deletion, right? But that one not for this semester, right? So some more examples to show you this. Wait. Okay, insert for 23. Okay, 23 will be inserted where? On the left of 28, right? Something like this. Then you update 23, have the balance factor 0, 28 plus 1, 29 plus 2. Oh, there is a plus 2 here. Plus 2. Plus 2 and my left subtree is plus 1. So I need just to do right rotate on 29. Then I will have this. Okay, right rotate on 29, I will fix that already. Now this is balanced again. Can you see that everything here is balanced? Balance means plus minus 1. Right? Now, after I have this, I insert 55. Where am I going to insert 55? On the right of 50. Right? By doing so, I will create 0 above 55 is 50 minus 1, and then above 50 is 65 plus 2. I have plus 2 minus 1 case. I need to left rotate here and then right rotate there. I need to left rotate on 50 first. I need to make it like this, right? Left rotate, and then finally right rotate on 65. Make it like that. Okay. So I have shown you FVL3. If you like computer science, you may have noticed that this is not the only way to create balanced tree. There are many other trees after that. So 1962 is the first actually. Then we have other 1972. We have B trees. We have red, black, splay, trips, and so on. These are some ideas of those other variants. I will just show you briefly. I will not discuss. Okay. All of this ends up with log n eventually. They can't do better than log n. But if there are certain specific requirements, then some trees can be better than FVL. FVL is more general. But most of them, they will run in log n for most operations. So a quick few slides to close the lecture. I said that rotate left and right manipulates several pointers. So what is the complexity for that? Just a quick one. Okay, 25, good enough. It's O1. And because of this is O1, rotation does not matter in terms of, it does not increase the time complexity of insertion, which is still log n. So after insertion, it's log n, right? You rotate something, but this rotate is just O1, so it doesn't affect the overall complexity. Next, every insertion requires at least one rotation. True or not true, I don't know. So is it true that every insert will need to do at least one, maybe sometimes 2 rotations? Is it true? Or maybe sometimes 3 rotations or something like that. Is it true? No, correct. Because some insertion does not change the balance factor, so you don't need to rotate anything. Can be 0, right? Can be 0. Can be 1, maximum 2. Left, right, left. A tree is said to be balanced according to Ederson-Felsky if every vertex children differ in height by at most 1. Yes, no, or I don't know. I have a vertex. Have 2 children, or I have children. Their height differ by at most 1. And I said my tree is balanced. Is it true according to Ederson-Felsky? Yep, it's true. And this is the definition of Ederson-Felsky tree. Variant. A tree is balanced if every vertex either has 2 children or 0 children. True or not? No. It's getting harder. This one is getting harder. A tree is balanced if every vertex either has 2 or has 0 children. I say no. Why? You can draw node 2 children, 2 children, 2 children, 2 children, 2 children, but you don't take care of the right one. Then it will not be balanced. So we end this lecture by this. I stopped last week by having BST all OH mostly, right? But now using AVL, I can show that this is log n, right? So if this is log n, your PS1 can be faster also. Okay. I will only show you a bit. So if you want to do PS4 subtask, PS1 subtask 4, you may have to do something like this. Okay, okay, close. So you need to implement rotate left and rotate right, and you have to do insertion. You don't have to do deletion. Why? Because there is no delete suggestion. Okay. But do you have to use such a very long code every time we need a balanced BST? You attend your lab demo, and you will next week your lab session. Not this week. Next week your lab demo will show you that Java already has a library code for it. Okay. That's all. So next week we will discuss heaps data structure. Bye bye. Okay, if you want to stay back, do this.